Yeah, hi, good afternoon. So today what we will do, we will finish this chapter, and if time permits, we will go ahead with the next chapter. But before I start for the lab, you might have already seen the survey that I have included in the announcement. So please accomplish that survey and send it to Dr. Makare. We want to do it as fast as possible. The reason is that when you go to the lab, you can pick up the kit. And if you pick up the kit by yourself, you are actually avoiding the shipping charge. So if you want to avoid the shipping charge, please make sure you reply to the survey and get your kit ready. So now what I will do, I will go ahead with the addition polymerization. So we will get started from the termination because we ended our talk at the termination step. So if you recall in the last class, so if you see in the last class, we discussed that the termination could be by combination, disproportionation, combination with the initiator, or due to chain transfer to the monomer initiator or the solvent. So all this, if there is a chain transfer, you end up with broader molecular weight. And sometimes you end up forming telomers, which are really very small size polymers. But one transfer, which is chain transfer to the polymer, is desirable if we decide to make branched polymer. If we decide to make branched polymer, this is desirable. Why? Let's take the example of polyethylene and we want to make LDPE. So we have to induce branching. So this is your polyethylene chain or all CH-CC bonds. You have a active monomer radical, or it might be an active polymer radical, whatever. Now, this, if you knock out this hydrogen, which is somewhere in the middle of the chain, what you are doing, so this hydrogen will go and quench any of these radicals, and you are generating a radical not at the end of the chain, but somewhere in the middle of the chain. So now when another growing polymer or another comes, it can combine with this and you have a polymer chain in the center, or there might be another monomer which can come and combine with this, and this monomer can further polymerize from here. So whatever you are doing, you are making the chains from the backbone of the existing polymer, not from the side. And this is giving rise to branched polymer. So this is how the termination takes place. Now termination, as I told you, unwanted termination is not desirable because unwanted termination can give very high PDI or very short chain. And you might also recall I told that it is very, very difficult to get PDI equal to 1. It happens only in nature. And if you want to have PDI equal to 1 in the lab, you have to ensure that you are making a living polymer. What is a living polymer? living polymer means which will not terminate. So it will go on growing. And this is only possible if you do not have any chain transfer or termination. So if you can really control your reaction, and this is generally done by the polymer chemist, you can control your PDI. Just hold on for 1 minute. Okay, it's fine. Then I'm not going to discuss the kinetics. I'm showing these equations to draw some conclusion. Now, first we are talking about rate of initiation. So what is rate of initiation? We know each eye is making 2 R dot. And it depends on the rate of dissociation. So, and the rate at which this is disappearing depends on this. More I you will have, more I will disappear per unit time. Or you can convert it in this form. Similarly, you are forming R dot. Now, the rate at which R dot will disappear will depend on how much R dot is forming. And how much R dot is forming is dependent on I. So I can write the rate at which my R dot is disappearing is proportional to I, but I am putting 2 kd because each I gives 2 R dot. So this is one equation. Now, once this R dot is formed, it has to attack the monomer where you form M dot, and this is the initiation step. So M dot formation is dependent on the rate of disappearance of Ri. More Ri disappears means more this form. And the rate at which the Ri disappears is given by this equation. So I can write the rate at which this is disappearing is proportional to minus R dot. And I know this is the equation, so I can write let me try to write here. I'm not using the parenthesis. But now the question is, what is this? Why I have this? If you recall, I told you guys that not all the initiators are taking part in polymerization reaction. Many initiators are getting wasted by cage reaction or induced decomposition or termination to the initiator, all these things. So to take into account this, I'm introducing F, which is radicals that initiate a polymer chain divided by radicals formed by initiator. Now, could you please tell what should be the value of F? What could be is it equal to 1, less than 1, or? Please enter into the chat box. Yes, all of you gave the correct answer. Very good. It is always less than 1 because numerator will always be less than the denominator. So hence you have this F in this equation. And this expression is Ri. So you can see more the waste, less will be Ri. Because more the waste, less will be the value of F. Hence, less will be the value of Ri. Then comes the propagation. Again, propagation means, if you can see, all these radicals are attacking M. So it depends on the concentration of this and this. This is the constant. Or I can write Rp is equal to rate of disappearance of M, which depends on the concentration of both or multiple. To make it an equation, I am putting this constant. Then termination. Now, in this particular case, I am talking about the termination only by combination or disproportionation. So what is by combination or disproportionation? How the termination takes place? So RT is equal to minus dm by dt, because which is equal to 2 kt m square. I can, instead of writing my mx, they are the same. I'm just writing mx, which is m square. Now this kt is ktc plus kd. So if it is only by combination, this is 0. If it is by disproportionation, this is 0. Or if it is a combination of both, this is kt. Now, I am focusing coming here. So the rate or the length of the chain is determined by Rp by Rt. How? Can you tell me if my Rp if it is Rp greater than Rt, will I get telomers or the long chain polymers? Please enter into the chat box. If my Rp greater than Rt, will I get long chain polymers or the telomers? Enter into the chat box. Yes, all of you are correct. I will end up with long chain polymers. But if it is Rt greater than Rp or Rt is equal to Rt, I will get shorter chains or telomers. So degree of polymerization, which gives the length of the chain, depends on the ratio of Rp and Rt. Or this is called kinetic chain length. So dp is directly equal to kinetic chain length if there is disproportionation. If it is combination, now two chains are combining. So now dp is 2 mu dot dash, which in turns and again dependent on Rp by Rt. So we have discussed the 3 steps of polymerization reaction. Now what we are going to discuss, I am going to introduce another term. And this is something the students get confused. I'll not repeat later on, but I want all the students to understand it right now. The term conversion. Generally, it comes, generally the students associate conversion with how much polymer is formed, which is wrong. Conversion means conversion of monomer to M dot. So this is called conversion, not the formation of polymer. So a typical graph of conversion or percent conversion versus time goes like this. So initially you can see more and more of this is formed. And later on, as the monomer amount decreases, less of this is formed. So it sort of plateaus. But if you have, we will not discuss the retarder. We'll talk about the inhibitor. If you have something called inhibitor, it follows. So initially, we'll see there is no conversion, and then it goes up. So what is inhibitor and why we need it? So as the name suggests, inhibitor means it is inhibiting. And what it is inhibiting? It is inhibiting formation of this. Now, why the formation of this radical is not desirable? Now, formation of this radical is desirable only when you are doing your desirable reaction. But unfortunately, what happens? Once you form the monomers directly doesn't come to you. And when it comes to you, there is no guarantee that you will use it immediately. So the monomers get synthesized in some chemical plant. They get transported. It stays in some bodega for a long time. And after that you use. So during the course of transportation and storage, there is a very good chance that, and remember that you do not know, you are not storing it at sub-zero temperature or something like that. So there's a good chance that over time, some of this might become this. And once few of them becomes this, they will start attacking other monomers in the reaction, in the container in which all of them are stored. So they will make undesirable polymers. Not only that, they might even cross-link this undesirable polymers. So whatever it is, you can see, like it happened with us many times, like we had styrene stored, we thought we will take it out for the lab. After 5 years, when we took it out, it was nothing but a gel, because inside all these reactions has taken place. And if this happens, then you have to simply discard that bottle of monomer, because it is not advisable to filter out the monomer from the polymer. It is not easy to do. So you discard the bottle and place order for the fresh bottle. So it is wastage. Now to ensure that M doesn't become M star during storage or transportation, you add inhibitor. So what is inhibition? So you have this, you include this type of species, but in very small amount. Now this species can easily cleave this bond to generate the free radicals. The chemistry guys, you might be knowing very well that once this radical gets generated, it can stabilize itself. So there is an incentive for this to separate. So in the system, by any chance, if you generate this, at that same temperature, this will also dissociate to form this, and this H will quench this. So now there is no more radical for the propagation of the chain. This can combine with another of its same kind, or it can quench another radical. So whatever it is not allowing the formation of M dot. Hence you can see it is zero here. Now, what is happening? Now from here, what is happening? It is increasing. Why is it increasing? because the inhibitor, you've put it in a very, very small amount. So if you're storing it for a very long time, at one point, maybe all these inhibitors will get used up to quench this M stars in the reaction. And after that, there is no more inhibitor in the system. So that is the time you can see this conversion. So if you are using a monomer, unsaturated monomer, it comes with the inhibitor. So you have to always distill or do some kind of separation to ensure that you do not have not the initiator, inhibitor, you do not have the inhibitor in the system, and the reaction picks up like this. The next thing that I would like to bring to your notice is GL effect. It is also called Tromsdorf effect, Norris-Smith effect, or autoacceleration. Unfortunately, we do not remember from these names, those who got these reactions, but we remember this as gel effect or autoacceleration. Now in the lab, students often encountered this, and it is fun. Fun for those students who did not get it, because they can see what is going wrong. But the students who get autoacceleration, I ask them immediately to stop the reaction. And they are not allowed to do the reaction anymore. So why this happens? So first, let me tell you how so you are stirring the system. At one point, you see, and it happens very abruptly that it is the stirrer is moving, and suddenly, like, stirrer is stuck. Nothing is moving. And I tell the students immediately to stop the reaction. Because if you try to continue it further, there could be an explosion. Touch wood, as of now, we did not experience any explosion. So why this is happening? And this generally happens if you keep the temperature higher or the monomer is too reactive. So ideally speaking, the conversion should follow this graph, which we discussed just now. But when there is autoacceleration, you will see a sharp jump in conversion and then it stops. Boom. Why? Now it happens if the reaction is going on too fast, you might have too many polymer chains. You might have some polymer chains, long polymer chains, and still you have lots of this residual M or M dot. So if this happens, because now you have polymer chains in the system, the viscosity has gone up tremendously. And because the viscosity has gone up tremendously, these polymer chains, which are relatively long, they are not able to come towards each other and terminate this reaction. But this is, since this is small, this is mobile, this is moving and adding onto the chain. So the conversion is there, but these chains are going slowly towards this to do the reaction. So as a result, the system becomes highly viscous or gel, or since there's a rapid rise in viscosity or percent conversion, it is called autoacceleration. And if the viscosity goes up, then what happens? Lots of heat generate in the reaction container. So unless you have a very efficient stirring system to dissipate the heat, this heat might ultimately cause explosion. So now you might ask, since this is giving very high polymer chain with the less probability of termination, why can't we use autoacceleration? No. In spite of getting high molecular weight polymer, autoacceleration is not desirable. One, because of the safety issue. Next, at one point it happens that even this cannot move anymore to the polymer chains. Because the polymer chains are so long, the reacting end might be embedded somewhere. And because of the high viscosity, the monomer cannot attack this. So when you filter, you find lots of residual monomer also, which is a waste. So as a result, you are not supposed to have auto acceleration. Later on, I will tell you only there is one case where auto acceleration is desirable. Then, as I'm telling you, I'm not doing hardcore polymer chemistry. I'm just showing you some of the things that you might encounter while doing a reaction in the lab. All of us are aware of this equation from PChem lab. Now, can you tell me what should be the sign of delta G and delta S for a reaction to be feasible? Can you specify which one you are telling negative? I'm asking sign of delta G and sign of delta S. So I'm not able to make out which one you are telling negative, which one positive. Yes, all of you are correct. For a reaction to be spontaneous or feasible, delta G has to be negative and delta S has to be positive. Then only the reaction takes place. Now, when you are doing polymerization, delta H is negative because the reaction is exothermic reaction. But delta S is negative too, instead of being positive. Why delta S is negative? So delta S positive means, is it more randomness or less randomness? If delta S is positive, is the reaction becoming more random or less random? Please enter into the chat box. If delta S is negative, the reaction is becoming more random or less random? Yes, if delta GS is negative, that means the reaction is becoming less random. And we always want the reaction to be, because we want more chaos in the system. So if you're converting A to B, randomness of B is expected to be more than A, so that delta S is positive. But polymers, they are already quite random. So going from here to here, you are not increasing, contributing to the randomness. So delta S is either 0 or negative. So if this is negative, so if this term is negative, this becomes positive. So as long as this is very, very high, your delta G is negative. But if you are doing the reaction at very high temperature, then at one point this might be more than this. In that case, delta G is positive. And if the delta G is positive, then this will be not negative. This is more positive. This is more positive. So delta G becomes more positive if you increase the T and depolymerization takes place. So G from negative, as you're increasing the temperature, G from negative is going to G positive. At a certain temperature, delta G is equal to 0 when these two values are the same. Delta G value is equal to 0. So in that case, That is called sealing temperature. So if your reaction exceeds sealing temperature, the reaction will stop and your degree of depolymerization, and at sealing temperature, your degree of depolymerization and polymerization will be the same. And above that, you will get more of depolymerization. So why I told these things, the auto acceleration and the sealing temperature. Now you might think, I told you higher the temperature, faster is the reaction. So you might think, why can't I raise the temperature? Do the reaction at higher temperature, my thesis will be done, I'll be done with the lab. I can quit easily. No. If you increase the temperature, there is a chance that you might end up having auto acceleration or you might hit the sealing temperature. So to expedite the reaction, though temperature is an option, but still there is the limitation of increasing the temperature. So you cannot just go on increasing the temperature as much as you want. Now, so I have discussed the very fundamentals or basics of addition polymerization. I will not extend beyond this. Before I end addition polymerization, let me show you that you can also work with this type of systems. So here you have unsaturation. So if you have this type of unsaturation, obviously you are making the linear or branched polymer. Now, if you have this, they mainly act as cross-linker. How? Now, for example, in a system, you have these monomers. And you also have. So they can undergo polymerization by themselves. But at the same time, if you have this, now if you start the reaction, this will open, this will open, this will open. So all this are opening up. So as a result, what has happened? This chain was growing, but at the same time, this is getting connected to this. This is getting connected to this. This is going. Oh, sorry. This is also getting connected. This is also getting connected. So you can see there are two growing chains, but they are interconnected. So there is a cross-linking. Then you can have this type of monomers where there are two unsaturations. They are mainly the rubber. This is the monomer of the rubber. So if you see, and you have to remember this because we will come back to this later on. When this undergoes polymerization, so this opens, this opens. Now this attacks another monomer, this attacks another monomer, and this two will form a bond, which is the double bond over here. So there you will have a polymer chain, but with a double bond. And this is mainly, this is all the rubber mainly the rubber, the natural rubber monomer, which undergoes this type of polymerization. So I still have time, but I will stop here. The reason is that I want to have the same pacing for both the classes. Now, before I end, is there any question?
Yes, ma'am. I just wanted to clarify what happens in the sealing temperature. So from what I understand, the depolymerization happens at the same rate as the polymerization. So the um, the molecules break down at the same rate, or like at that temperature, there's enough of the monomers breaking down to counter like the reactions of the monomers to form polymers.
Okay. So let me tell you my own experience. You might find it boring, but I still remember. It was almost my first week, maybe around first week of my PhD thesis. Here you get started late, but in US, the moment you have your advisor, immediately, instead of telling hi, hello, you are shown the lab, more or less. This is your work area, you have to get started. So I was trying to make a polymer. So 1 week, 2 weeks, every time I will make the polymer, it is at the end, I will not, while doing the calculation, I will not getting the yield beyond a certain percent, and I'm ending up with lots of monomer. It was quite frustrating for me. That time I was not aware of sealing temperature. So I thought like I can impress my advisor, keep the temperature high, get lots of polymer, and boom, get your PhD in 1 year or so. Maybe that was my idea. God knows what. So I was doing the reaction at elevated temperature, and it was not happening. And later on, I found out that I was actually hitting the sealing temperature. So if you hit the sealing temperature, you will not, like sometimes you do not get high yield because you are not doing the reaction for adequate time. But if you're doing the reaction for a long time, but still you are not getting high yield, and whenever you are separating, you have the monomer and the polymer in the system. But remember, these are the longer polymers, not telomers. If it is telomers you see in the system, that means you are having chain transfer. So there is a difference. So that time I realized that it is the sealing temperature. So sealing temperature, you will have the polymer and the monomer always in the system, because polymer is forming at the same time, the monomer is also forming. So there is a kind of equilibrium. Is it clear, Lance?
Yes, ma'am, very clear. Thank you.
Any other question? Cheska, you are telling February 23 recording is inaccessible. Oh, maybe, I do not know. Maybe the video setting is wrong. Thanks for bringing it to my notice. I will go and check the setting. And if, or I might re-upload it. So I will check it out soon. Okay. Thank you. Any other thing?
Doc, is the quiz next Wednesday already synchronous?
I told you that always I'll be announced at the last moment. So you have to always remain prepared. Yeah.
All right.
Yeah. That is the challenge. Any other thing? Okay. So I will then see you guys on Friday if there is no question. And Cheska, I will check it out. What has gone wrong? And if still there is any problem, let me know again on Friday. If you are not able to access it. Okay. Okay. Thank you very much. See you guys on Friday.
Thank you, Doc.
Bye.
Thank you po.
Thank you.